So thank you very much for the introduction. Indeed, I have some molecule examples in the presentation, but I will focus on low energy electron microscopy, which I found that it's really amazing instruments to see what's on the surfaces. It complements to the very microscopic view introduced by Franz Giesibel, and it goes more to the mesoscale. So I will introduce briefly LEEM, then I go to the sub-techniques of the LEEM, like bright field imaging, diffraction, dark field imaging, and you will really see that this instrument is worth to consider for your studies. So for the introduction, the LEEM, it looks like any, from outside, any vacuum instrument. It's piece of stainless steel, but important is what is inside. So we put our sample there, and by the electron gun, we form parallel beam of electrons, which are coming to the surface of the sample. So we are not scanning, we are really imaging what's on the surface. Importantly, there is a magnetic prism which turns electrons to the sample, so we can then study the reflected electrons which are coming out of the sample. So we just need bulk samples. The technique is slightly similar to transmission electron microscopy in what we can do, but we just emit the surface with low energy electrons, not high energy electrons. Then the beam is reflected from the sample, it's turned in the sample prism again, and then my imaging arm is imaged on the detector. So in this instrument, we have access to both real space, so we can do surface imaging, and reciprocal space. The difference is that here in the backfocal plane of the image, there is a diffraction, so just by switching off one lens, we directly see the diffraction. So for the sample, this is on negative potential, it's 15 kilovolts as well as the source. But if we adjust a bit, so we do not decelerate electrons completely, but to very low energies in range of 0 to 100 eV, which is most useful range for us. The beam spot, we can view the sample, it's like 10 to 15 micrometers area. We can go to lower to enhance the resolution. And using the special apertures in the design, we can access the micro diffraction, which I will talk in a second, and also dark field imaging, which are really nice advanced techniques. So I will show you really the molecules on the surface. So for this presentation, I will introduce several experimental systems. One is of this molecule, this biphenyl dicarboxylic acid on the silver 100 surface. So first, what we can see is the real space view. There we can see molecular islands which appear in black and bare surface which is bright. And then we can easily switch to reciprocal space. In reciprocal space, for example, we can identify substrate diffraction spots, and all other molecular spots appear in addition to the substrate. I will go in detail to the presentation. Then the specialty is the micro diffraction. We take the aperture, its diameter down to 200 nanometers. We select the area which we illuminate with the electron beam, and then measure diffraction really from one of these small areas. So if we measure different areas, we see two distinct diffractions. For the single molecule phase, which are the rotation domains, we can do composition compared to over diffraction. Then with another set of diffraction apertures, we can put this to the diffraction pattern and image sample only to one of those diffraction beams. So this is the overview. So if we put the aperture here for this diffraction spot, we see mainly one of the orientation of islands. Then the second diffraction spot, the second orientation of islands. Then if we color code, we can distinguish islands according to their orientation. So the nice thing that we can do real-time imaging, we can see what's happening on the surfaces. And the important aspect is that we can combine with scanning tunnel microscopy in single UHV. So we have complemented to this mesoscale view also atomic scale view and also chemical analysis by X-ray photoelectron spectroscopy. Really, the low energy electron microscopy profits out of those techniques which are quite necessary to really understand what's happening on the surface. So now we can go more into detail in the techniques. So first, bright field imaging. So actually we image electrons through the OO spot, which is like specularly reflected from the sample. And there are several contrast mechanisms we can utilize. It could be like material contrast or morphological contrast, which is due to electric field inhomogeneities or the difference scattering amplitude. For example, here we see molecular islands on the bare silver substrate. The second contrast mechanism is interference contrast, where we can see the atomic steps or different thicknesses of the materials. In this example, we really see every atomic step on the surface, which is very advantageous. So we can then consider what's the role of the steps for the molecular systems on the surfaces. Then the real advantage is this video rate imaging. We can get spatial resolution below 5 nanometers, and we can do all that during the sample annealing or deposition, exposure with gas and everything. So this is example from this molecule system where we have two different phases of molecules, and one is transformed to another at this temperature. So initially we see only the first phase, and then in this video we mark in green what's growing and in red what's dissolving. So let's see how it proceeds. So first there is some nucleation of new phase. It quickly enhances and the old phase just evaporates to the molecular gas which is on surface. Then to this molecular gas, the molecules are transferred to new growing phase. So this allows us to consider how these molecular systems are transformed and see the kinetics, and with combination with theory, we can derive some dynamics of this molecular phases evolution. The next example is from the similar system, but at high temperature, we already have the second phase, which then transforms to third phase. In this case, if we have a lower molecular coverage, we see that the new phase nucleates in the old islands. And then if we expose the islands to free surface, there is a rapid growth. So it's marked with the arrow. So here, if we expose the islands, the new phase quickly grows because the lot of molecules are in the molecular gas. And you see, first, with increasing temperature, the molecules, you see again, the islands are diminishing, the molecules are evaporating to surface gas. And then once this nuclei of new phase is exposed to surface, then it quickly grows from the available molecules in the molecular gas. So then we can do more. We can do more from just, if we record the contrast of the island as function of the energy. We have the accessible energies we mostly use from 0 to 20 electron volts. And then if we record, we see that the intensity and also the contrast between stages or the islands and the substate or different phases of the molecules changes from with energy. For example, here at low energies, the surface is always brighter than the molecular islands. But at certain energies, there is not much contrast and it could be even reversed, like here. So here we see one phase which is similar contrast to surface. So with this, we can identify most suitable energies to image the molecular phases. But of course, if you see this curves, it would certainly remind you the advanced dynamic lead analysis where you can really do atomic positions from the calculations. In the next example, it's not still there, but it's getting close. And this is the second experimental system, which is the silicon carbide hosting graphene layer, and there is some buffer layer. So we can do this function. There we see that we have different part samples which shows different energy dependence. So which just change the energy here and see that the islands are changing the contrast. And based on this, we can identify that the majority of the surface is single layer graphene. Some parts are 2-layer graphene, and in some parts are 3 or more layer graphene. So how we can say that? If we record this curve, this is from the single layer, then we can do the same. We are just changing the energy and then recording the intensity of the particle parts. So it's like this, changing energy, and then we record the intensity. So this is for the single layer, this is for double layer. For 3-layer graphene, it's the blue one. So for single layer, we see a single minima, because for 2-layer, it's 2 minima. For 3-layer graphene, it's 3 minima in the curve. So this is this result of this interference contrast. And so this really allows us to see how many layers of graphene we have. Example, if you want to see 2-layer graphene where it is, we change the energy below 4 eV, something like that, and we see that only 2-layer graphene appears bright in the image. So we can do similar for other stuff. Then we really can map how the process of making silicon carbide is, how many there is single layer, and we can do quite quickly the statistics for we can even do it during the process, many things. So nice part of LEEM is that we can combine it to diffraction and even micro diffraction. I will show you one example from our molecule system. So there the diffraction patterns can appear quite complex. And this is just to remind that we see the diffraction from periodic structures where the diffraction condition is fulfilled. So we see actually the image of the reciprocal space. And in LEEM, we have access to the diffraction pattern just in back focal plane of the objective lens. So we can image that easily, and we can switch from the real space to reciprocal space in less than 1 second. So we can watch what's happening, check the refraction pattern, then also again watch the real space. So this is the diffraction pattern at 20 eV. We have the advantage to take the STM image from the same structure. So here we see how in real space it looks like, which is quite necessary to correctly assess the diffraction pattern. We can even in collaboration do this nice atomic force imaging introduced by Franz Giesebel So there you can see that the unit cell could be made from 2 molecules in each unit cell, and it has this size. But let's see that it's really not exactly the case here. So the complexity of these diffraction patterns comes mostly from the surface symmetry. So for this substrate, it's the 4-fold rotation symmetry, and we have several Meyer axes. And if our molecule is sitting on the surface, not aligned with surface, we have 4 possibilities. And we have 4 possibilities. Then we have 4 rotation and symmetry equivalent domains on the surface. So then we can see in this diffraction pattern actually is composed of 4 different rotation domains. Fortunately, we can make smaller aperture and measure the diffraction only from small areas on the surface, and we can see 4 distinct orientation of the diffraction. The patterns are the same, but just have different orientations. So then we can make this composition of those micro diffractions, and we end up with the full diffraction pattern at the end. So taking the STM, taking the micro diffraction, we can see the reciprocal unit cell, but we see there is something more, that it's not the pattern itself, that it's smallest parts, the 2 unit cell. And also the size, it's not easy in LEEM because there are some image distortions in the diffraction pattern, which prevents you the quantification, that you measure the distances and calculate the unit cell. So we have to do something, go somewhere around, and then we can take the advantage that we have so many spots. So first we decompose the patterns. So we have the substrate spots, the molecule spots, and we even see those spots which are like Moira-like spots, which in between those. And this is the composite pattern. And here we see that for different domains, we have spots which appear close together. So we take utilization from that if we slightly change the unit cell, that the mutual position of this spot will be different. So we take this decomposition and simulate the diffraction pattern, just basic kinematic approach. So this is the measured diffraction, this is the simulated pattern, and to optimize, we have to consider this unit cell, not the one we directly took from STM, but slightly different one. And then we can select few areas just to make better composition. So these are imaged here, and we really see that if we calculate, the mutual position of the spots is almost the same as in the measured diffraction pattern. Now, if we consider slightly different unit cells, then we see that the patterns are really not matching. So now we can be quite sure that this is the correct unit cell, just based on the mutual position of the spots from different domains. And so it's the final unit cell, it's this one. This is the unit cell determined from STM. So it's bigger, and it could be important for the properties of the molecule domain. Then we can go back to STM and select the areas which should be equivalent from this unit cell, enhance contrast, and we really see that in all those parts, the contrast of the molecules, the minor contrast, it's almost the same. So we are quite confident that we find the correct unit cell. And the final part is so-called dark field imaging. So dark field imaging is that we do not use the spectrally reflected beam to image the surface, but we take one of the diffraction spots, which we put aperture in and only image to this aperture. Then, going back to our molecular phase, we selected 4 spots from different domains, and then we image only 2 the spots. So now the image, this is the complete image, and image to the spot is that. So we see only several islands which appears bright. We take blue one, we see those 2 islands. The red one, there are more orientations, and for the green one, those. So again, we can color code and put finally to the composite image, and we can really distinguish in islands what's the orientation of the molecules within these islands. If we would have multiple phases, we can do the same for multiple phases of the molecules on the surface. But then, of course, it would be more complicated. Then we can have like 4 orientations for one phase, 4 orientations for second phase, and all will add to single diffraction, and then we can distinguish what's there. The second example I took is from the system when we have iron selenide or bismuth selenide. Bismuth selenide has hexagonal structure and it has the quintuple layers. So the diffraction of the bare surface is quite simple. You have hexagonal structure. If we select some particle energy, 3 of the spots appear brighter for one orientation, while the one domain of the substrate, 3 other spots appear brighter for second orientation domain. This is due to this hexagonal stacking. But let's come to iron selenide. If we have iron selenide, we take this substrate, deposit iron, and in the resulting structure, we still see the substrate. We can slightly change the energy to see more clearly the overlayer. So here we still see the substrate spots, which are now here, those, and then the overlayer spots, which is for the iron selenide. So iron selenide has 3 equivalent domains, which are square domains on hexagonal substrate. And then if we identify the spots here, we can proceed to the dark field imaging. So then we make dark fields to these equivalent spots. And then locally, we can distinguish that we have domains with size well beyond 100 nanometers. So this is very nice to do statistics, how the overlayer is formed, what the size is, how it's limited, if we can image step edges, and so on. You can even see that some carbon residues on the surface from the decaying procedure. And again, we can compare with STM, and we really see that the islands are sub 100 nanometers, while the surface has larger terraces. So now this GO is just limited by the nucleation of the new phase, not the domain size. It's by the substrate. So in LEEM, we have also other modes, which I will briefly only in one slide, just they are existing because we are getting close to the limit of my time. So in the LEEM, in the magnetic prism, it actually works as an energy filter. So we can do energy filtered imaging and do some kind of RPS, even with not such high resolution, but we can do it spatially resolved with the resolution of the LEEM. So we are starting to working on that, to going more inside. We can have different photo emission electron microscopy when we use UV sources as the excitation source. So we can do that. So with that, I just would like to summarize that I hope that I showed that LEEM is powerful technique for surface science, which allows you to go to mesoscale, not really the microscopic view, but the larger view. We can have several techniques which allows us to track the changes in real time, precisely determine unit cell, to say how many graphene layers we have, to do statistic of orientation, size, imaging. Also in future, we will do some energy filtered and advanced techniques. So it's everything. I would like to thank my group and the projects we have for the support, and I will thank you for your attention. If you would have this time, so we can discuss everything. If you contact me with email, we can set some online meetings. So it's instead of meeting during the lunch break. So we can do that. So thank you for your attention.
Thank you very much, Jan, for this nice instructive talk and demonstration of such an interesting technique. And I have here one question in the Q&A section. I will read it. Yeah, he says that, or she says that, missed your the beginning of a lecture, and the question is if it is possible to image biopolymers like yours, and why the silver substrate has used in all imaging results. Why not other noble metals or other substrate?
So,
yeah? Okay.
Okay, actually, we use silver because we selected this as a model system. We can, with the same results, use other noble metals, but for a molecule system, if we put the molecule we selected for the target, then on copper, it will chemically change upon deposition. So we see no phase transformation. That would be quite boring results. On gold, it doesn't do anything. So, on silver, it stays in this metastable state, and we can do all this imaging of the phase transformation and see how they are transformed and all the stuff. One important thing, this is the second part of the question, is that we need UHV, and the UHV compatible samples. So we can, in principle, if the biopolymers are UHV compatible, then they can be imaged. The second important point, if we want to see diffraction, it should be crystalline, single crystalline, and also it should be clean. We try to use deposited graphene on the sample, but if was not possible to UHV clean, we couldn't see diffraction. And if you see diffraction, you lose half of this nice possibilities. You can still see some image, but if you see the same image you can see in standard electron microscope. So there is no advantage to take it into LEEM.